All right, so today we're going to continue talking about series, and I want to introduce a couple of tests that we can use to determine whether a series converges or not. So, recall from the last section that we defined an infinite series to be the limit of the partial sums. So we just keep adding on more and more terms until n goes to infinity, the number of terms goes to infinity, and we approach the 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 sum, right, of the sequence, which is a series. And if you remember, this formula that we ended up with looks very similar to the definition of an integral, right? And for an integral, we were adding up those Riemann sums, right? And we were adding up those little rectangular slices, and we broke the interval into more and more slices, and as the number of slices, went to infinity, we ended up with an integral. So this looks a lot like an integral. The big difference, though, is that n is just a natural number. It's not any real number, right? So they're natural numbers. But let's take a look at how these things relate. So in this diagram, you can see I've taken a function f of x, where now this is a function where a sub n is equal to f of n. Okay, so it's basically the function that defines the terms of the sequence. Only it's it's defined over all real numbers instead of just at the natural numbers. And I've taken a very specific case, right? This isn't just any function. This is a function where the function is continuous, first of all. So f of x is continuous. And it's also positive, right? It's above the x-axis, so it's positive. And it's decreasing. So it wouldn't make sense to look at an increasing function because obviously that's not going to converge. But if it's going to converge, it's going to be a decreasing function. So we're taking the case where it's decreasing. Okay, on the interval 1 to infinity, right? Because we're starting, our sum starts at 1 for n equals 1 and goes to infinity. So, the curve shows f of x, and then the rectangles here show the series, where the height of the rectangle is the value of the series at that point n. So you can see it looks like the way it's drawn, this is essentially the left-hand sum, right? So this is the left-hand Riemann sum. Let's see. Riemann, I think it's R-M-A-N, and I don't know, E-I-R-I, I can't think now. It might be E-I. So anyway, this is the left-hand Riemann sum, and and you can see that in this case where f of x is continuous, positive, and decreasing, you could see that the left-hand sum gives us an overestimate, right? So, and the series a1 plus a2 plus a3 is the left-hand sum, and it's an overestimate, so it's greater than the integral. Now, if we look at the other case, if we look at the right-hand sums, now we're only integrating from 1 to infinity because we're adding from 1 to infinity. So you can kind of ignore this a1 at first. If you take if we were to do the right-hand sum, so right-hand sum, to estimate this integral, we would start with a2, right? Because we're trying to estimate the integral from 1 to infinity, right? So we're going to start with a2 and add those up. So we can see that has to be an underestimate. a2 to infinity has to be an underestimate of the integral from 1 to infinity. But then if we just add a1 to both sides, then we get the complete series on the left-hand side, and then the right-hand side is equivalent to that. So we can use that to determine whether a series converges or not, because if this integral converges, then the series converges. You can see that the sum, where we've got bounds on the series now. It's bounded on the, let's see, it's greater than, right? The series is greater than, so they're bounding this on the bottom by the integral from 1 to infinity, and we've then bounded it on the top by a plus 1 plus the integral from 1 to infinity. So somewhere in between those two things, the series is somewhere in between those two integrals, right? Either the integral from 1 to infinity or a plus 1 plus the integral from 1 to infinity. So we have bounds now on the series, and if that series converges, or sorry, if the integral converges, then the series converges. Does that make sense? So hopefully I explained that well enough. So that's what we're calling the integral test. But it only applies to the specific case where f, the function, is continuous, positive, and decreasing on the interval from 1 to infinity. If that's true, then we can apply the integral test. If it's not true, then we can't apply the integral test. Okay, so the integral test, we basically just take the integral of the function that defines the series, right? So it's essentially the explicit function. We integrate that from 1 to infinity, and if it converges, then the series converges. And if the integral diverges, then the series diverges. So let's go to example 1 and apply this. So example 1 involves something called the harmonic series. Now the harmonic series is kind of just, it's kind of historically famously studied and it's called harmonic because it relates to the harmonics of plucking a string. So it is related to the musical harmonics, where if you pluck a string, you get a fundamental frequency determined by the length of the string. But then you get these resonant frequencies at that are 1/2 the wavelength, and 1/3, and 1/4, and 1/5, and 1/6. So so the harmonic series is basically the sum of 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. Okay, so it's just called the harmonic series. But that function 1 over n is, so it is continuous, right? And so we have to make sure that it meets the criteria before we apply the integral test. It's positive, right? Positive. And it's decreasing. Decreasing on the interval from 1 to infinity, right? So if that's true, then we can apply the integral test. And it's true, so we're good to go. So we want to integrate this from 1 to infinity, right? So what I want to do is actually, I'm going to integrate it from 1 to some arbitrary value t, and then once I figure out what that integral is in terms of t, then I could take the limit as t goes to infinity to get the improper integral. So I'm going to do the integral of 1 over x dx, right? And when I integrate 1 over x, right, I get the natural log of x, and I want to evaluate that from 1 to t. So when I put in t, I get the natural log of t, right? And then I've got to evaluate the lower bound, so I get the natural log of 1, right? And that's just 0. So essentially I've just got the natural log of t, right? And now what I want to do, I actually want the integral from 1 to infinity of 1 over x dx. So that is the limit as t goes to infinity of this result. Okay, I kind of prefer to write it this way just because then I don't have to write limit as t goes to infinity over and over and over again. So we're going to do the limit as t goes to infinity of the natural log of t. And we know that that is infinity. So therefore, right, so we can conclude from that, therefore, the series diverges. The series diverges by the integral test, by the integral test. Okay, so our conclusion is that it diverges. All right. Now this is one too. If we did the test for divergence on it, right, where we look at the nth term of the sequence, 1 over n does go to 0. So so if we tried to use the test for divergence, it would be inconclusive because the 1 over n, as n goes to infinity, does go to 0. So it doesn't fail that test for divergence. So we don't really know what happens. But it turns out that this does diverge by the integral test. All right, so you can see the next example is another another application of the integral test. Although you should always check before you get started. Make sure that it's continuous, positive, and decreasing on the interval from 1 to infinity. So always check that first and make sure that the integral test actually works. But you can go ahead and try this example too, and then I'll see you in the next video. We can go through it together.